Okay, so we are going to talk now about some additional techniques of integration. And you see here we have a trigonometric integral. It's called that because the integrand involves a trig function. And when you have this cosine fifth of x, that just means that's notation for cosine of x raised to the fifth power. Okay, and you know, you've seen, of course, in trigonometry some trig identities, but there's no identity that I know of that deals with the cosine of x to the fifth power. What about this identity here? What's the cosine squared of x plus the sine squared of x equal to? That equals 1. That's right, Claire. That's a trig identity. That's a trig identity. Okay, and so this particular problem, well, the cosine, and you know, we could think of this, of course, as the cosine of x quantity squared plus the sine of x quantity squared equals 1. Same, that's equivalent. So maybe what we could do is rewrite this integral a little bit so that we could utilize this Pythagorean identity. And that's what we're going to do. So let me go to the next page and I'll show you what we're going to do here. So I take this, yes, Susanna?
Hi, I'm wondering why we couldn't use u substitution, cosine x being u, and then take the integral of u to the fifth.
So if you did that, it's not, here's the issue with that. If you were to do, it's a good question, if you were to let u equal the cosine of x, okay, then you'd have u to the fifth power here, for sure. But then du would equal negative sine of x dx. And there's no sine of x in the integrand. So that's why it wouldn't work. If you had a sine of x in the integrand, it would work. Good try. But look at what we can do here. I can take that cosine of x to the fifth power, and I can write it like as cosine of x squared times cosine of x squared times the cosine of x. I can, you know, break that cosine of x to the fifth power down a little bit. And then the cosine of x squared, you see, I can get the sine function in there by the Pythagorean identity. Because if since sine of x squared plus cosine of x squared equals 1, that means that you know, we're familiar with this. That means that the cosine of x squared would equal 1 minus the sine of x squared. So you see, we can replace these cosine squareds of x. We can replace those with 1 minus sine squared of x. And that gets us down to this integral. Now that the trigonometric integral has a sine and a cosine in it, now I'm ready to make a substitution. Now we're ready to make a substitution. And the substitution we're going to make is u equals the sine of x. then du dx is cosine of x, and du is cosine of x dx. So we transform through that substitution the integral with respect to x to an integral with respect to u, the variable u. Now the limits change, of course. The pi over 2 here, okay, that limit, well, since u is the sine of x, the pi over 2 limit would become the sine of pi over 2, which is 1. And the x limit of 0, well, that then, under the u substitution, the corresponding u limit would be the sine of 0. And that's just 0. So now we get this new integral with respect to u, and it's a polynomial, right? 1 minus u squared times 1 minus u squared. I can FOIL that out. And so my new integral will be from 0 to 1 of 1 minus 2 u squared plus u to the 4th du. And now it's a calculus 1 problem, right? Susanna, question?
Oops, forgot to put my hand down.
Okay, no problem, no problem. All right, so think all this over for a moment. Let me know if you have any questions. Okay. Well, so now, if everybody's good, then let's just proceed on with the problem. And, you know, find the antiderivative of 1 minus 2u squared plus u to the 4th. So we're continuing here. Here's the antiderivative. That's like calculus 1, you learned that. And we're going to have to substitute in then the 1, the u limits of 1 and 0, which I do here. And when you work that out, you should get 8/15ths. And that's what WebAssign will want. Okay, so, yeah. WebAssign always wants simplified radical form, unless it says, give me a decimal. It'll want simplified radical form. Okay. Are there any questions at all? Okay. Let me go to the whiteboard, and I want to just look at another one with you. let's say you had something like this. Let's say you had the integral of cosine squared of 6 theta, which I'll put in parentheses, that's optional, 6 theta d theta. And you want to find the antiderivative. Well, for this problem, the problem we just did, we relied on a trig identity. And here, we're also going to rely on a trig identity. So the cosine squared, let's see here. One moment. One moment, class. So cosine squared of x, does anybody remember this identity here? From the trig days, seeing these kind of identities? Cosine squared of x is 1 plus cosine of 2x over 2. Okay, Mark remembers that. And actually, let me just show you in the ebook. I think it's worth showing you. One moment here. Just bringing it up here. Right. So Niyat, it would be this. Should be this one here. Let me go into the ebook. Now, where would you find, where would you find trig identities? Well, in the ebook, what you have to do, and you have access to that ebook through WebAssign, and then of course, if you have a physical textbook, you have access. You go to the appendices. You go to the appendices, and actually, let me just hold on. So there are a lot of appendices, there's a lot of appendixes, but we want the one on trigonometry. We want the one on trigonometry. So we'll select that. And you get then this Appendix C on trigonometry. And it really reviews trigonometry nicely. And if you keep sort of going through there, there's some of those right triangles that we talked about. It's really a nice review. There are some identities, and this is the identity that we're going to use here. Okay. All right. So you will have access to trig identities for your exam. I think students, if you were an engineer and you're trying to do integration, you would be able to look up an identity, trig identity, and I want you to have access to that. How many might want to be reviewing this trig section in Appendix C a little bit before the exam? How many might find that helpful? Okay, Clea Wood, wonderful. And Iberdeen, wonderful, wonderful. Okay, well now let's go back to the problem at hand. So let's go back to the problem at hand. I think I'm going to have to write down that problem again. So let me see. It was the integral of the cosine squared of 6 theta d theta. And, here's my trig identity. Cosine squared of 2x is equal to, no, wait, scratch that. It's the cosine squared of x. That will equal 1 plus the cosine. So Mandy, I'm going to work on that. Where would the trig identities be located for the test? I might have them on a sheet of paper for you. Okay, but one way or another, you'll have access to them. For now, of course, for your homework, use the back of the appendix in your textbook. All right, so the 6 theta is my x. So if I use the trig identity formula here, this is going to be then equal to 1 plus the cosine of some angle all over 2 d theta. What angle is going to go in here? What angle is going to go in there? Well, it's 12 theta. That's right, Gabrielle, because you have 2x here, and x is 6 theta. So this is going to be 12 theta. And so it turns out that we're going to have then the integral of 1/2 plus cosine of 12 theta all over 2 d theta. And you would break that up. You would break that up into the integral of 1/2 d theta plus 1/2 times the cosine of 12 theta d theta. And so you'd have 1/2 theta, and then you need the antiderivative of the cosine of 12 theta. I can tell you the antiderivative of cosine is sine, so that's just going to be sine of 12 theta all over 12. And then you have a constant of integration. Okay. So in the end, the antiderivative is 1/2 theta plus, let me see, one moment on that. 1/2 theta plus 1 over 24 times the sine of 12 theta, parentheses optional, plus a constant. Why the 1/2 twice? Because you have a you have the 1/2 here, but then you also have a 1/2 here. You see, and you can factor each of those out of the integral. So all I did here was I took the integral of the cosine of 12 theta. Okay, you're welcome, Claire. Over 2 d theta, and I just pulled out the half. So that's another example of so these trigonometric integrals, you have to kind of find the right identity to help you, and then you work it out. Now I want to do one more problem. With you, and this problem, we're going to use an approach called what's called partial fractions. So let me go ahead back to the back now to the regular slides, and this is all in the recording. This is why I like, I have the recordings available. They have everything in it. It wouldn't, if I shared like notes with you, it wouldn't be enough. It's better that you have a recording, a closed caption recording, right? That has everything in it. Okay, so I want you to copy this example down, and this is a very important example. Integrals like these, where you have rational functions, they come up a lot in differential equations, which is Math 282. Differential equations where, if we're trying to find an inverse, what's called an inverse Laplace transform, you have to do integrals like these. How many have to take the differential equations, Math 282? Okay, OPME has to. Okay, I'm sure a number of you do. I hope I get to teach that course again. I've taught it before. All right, let me give you a moment here. Okay, so when you look at this, when you look at the denominator, can the denominator be factored? Can we factor that denominator? I mean, 2x squared we know is 2x times x. What would the factors be?
Be -1 and +1.
That's right, Susanna. 2x minus 1 and x plus 1. So when you do when you do these kind of problems, you always have to have that denominator factored. You always have to have that denominator factored. So let me go to the next page. All right, I rewrite my integral I, where the denominator is factored. And what I'm going to use is what's called a partial fraction expansion. This rational function actually has what's called a partial fraction expansion. And the partial fraction expansion is here on the right side. Let me give you a moment to catch up here, and then I'll explain this a little bit. Okay, so in this rational function of 5x minus 4 over the denominator there, we factored the denominator as 2x minus 1 times x plus 1. And those are what are called linear factors, because linear factors have, they're polynomials of the first degree. They have degree 1. So, you have x to the first power here, right? X to the first power. So what I do is on the right-hand side, when I do the expansion, I put both linear factors there. Okay, I'm going to add two fractions. The denominators of the two fractions are going to be those linear factors. Now in the numerator, I have above the 2x minus 1 the constant a. And then over the x plus 1, I have a different constant b. So what happens is, because you have linear factors here, 2x minus 1 and x plus 1. Those are both of degree 1. Well, the constants that I put above have degree 0, right? The constant is a polynomial of degree 0. Because like if, let's say you have the number 5. Well, 5 is like 5 times x to the 0th power, right? So the rule is you put above on the right-hand side when you do the partial fraction expansion. If you have linear factors, you put in the denominator, you put constants in the numerators, because those are of one less degree. Let's say you had something like this. Let's take another analogy. Let's say you had in the denominator x squared plus 5. Okay, in a partial fraction expansion, you have x squared plus 5. Well, what would go in the numerator? You're not going to have just an a, because x squared plus 5 is of degree 2. So you have to have above it in the expansion a polynomial of degree 1. Well, that would mean you would have a times x plus b. Okay, so that's just an example, a different example. But let's not worry about that. Let's worry about the matter at hand here. So okay, so I mean this was correct, but I just don't want you to think about that right now. So okay, so here we are. Now this is a rational equation. And I want to find out what those constants a and b are. So I have to simplify that rational equation. One way to do it is to multiply by the 2x minus 1 times 2x plus 1. Okay, that's called your LCD. Okay, LCD stands for what? LCD, you remember what in pre-calculus? How many remember working with rational equations in their pre-calculus days? Okay, Daniel remembers. And what does LCD stand for? Least, right, lowest or least, that's right, Nia. Lowest or least common denominator. That's what it stands for. And so I'm multiplying through the equation, all the terms, by that least common denominator. And this parentheses here should just be small, right, on the left there. Hold on, let me just, this isn't a big parenthesis. That's a small parenthesis there. Okay. And, we're multiplying through. And why do we do this? Why do we multiply through that rational equation by that least common denominator? Well, some nice things happen, right? Some simplification happens. Here, 2x minus 1 simplify, and x plus 1 simplify. And so on the left-hand side, I'm left with 5x minus 4. On the right-hand side here, well, 2x minus 1 simplify, and I'm left with x plus 1. And then on that expression on the right, the x plus 1s simplify, and I'm left with 2x minus 1. And so now I've turned this rational equation into a nice equation. And I want to solve for a and b. I want to solve for a and b. Are there any questions? Are there any questions up to this step right here? Please let me know. All right. Okay. So, well, so the natural thing to do now is to distribute the A through the x plus 1 and distribute the B through the 2x minus 1. That would be the natural thing to do. So let me go to the next page if we're good and continue the problem. Okay, so again, I have this equation. I want to solve it for A and B. I'm going to distribute the A through the x plus 1, and I'm going to distribute the B through the 2x minus 1. That'll give me on the right side ax plus A plus 2bx minus B. That, of course, could be written as ax plus 2 times bx plus a minus b. Well, the ax plus 2bx, we can factor an x out on that, and so that's going to give us this expression, the quantity a plus 2b times x plus a minus b. Well, a plus 2b times x, right? So now we get to this equation here, and we have to solve for a and b. Well, the left-hand side has to equal the right-hand side. So that means the coefficient of x on the right-hand side has to equal the coefficient of x on the left-hand side. Therefore, a plus 2b must equal 5 if the equation's true. Similarly, the negative 4 on the left, well, that's a constant. Well, that'll have to equal the constant term on the right, a minus b. So a minus b equals negative 4. So look at what we have now. We have two equations with two unknowns, a and b, and we can solve those either using substitution method or the addition-subtraction method. Well, I'm going to choose to use the addition-subtraction method. So I want to cancel out the b terms. So here, where I have negative b, I want a negative 2b. So I'm going to multiply the left side by 2. And then the negative 4 has to get multiplied by 2. And this is then the resulting equation here. I add both equations. The b terms cancel out, and I get 3a equals negative 3. Therefore, a equals negative 1. Absolutely amazing. Well, if a equals negative 1, then I can substitute a equals negative 1 in either of, the two equations here. all substituted in the second equation. So when a equals -1, well, the second equation is a minus b equals -4. I'll just substitute a equals -1 for a in the second equation. I chose the second equation just because it looked a little easier to me. And, you know, so -1 minus b equals -4. So b would equal 3. And now we're able to write the integral of this rational function, okay, as the integral of the sum of two easy rational functions. And this is called a partial fraction expansion. Are there any questions?
Would we plug it into WebAssign in that form?
Oh, well, we're not done
We're
yet,
not done.
Susanna,
Oh, okay.
because we still need to get an antiderivative. We did find a and b, and that's good, but now we need to continue the problem. But you can see that the right-hand side, the right integral, is, you know, much easier to work with than the integral on the left. I mean, they're the same integral, but well, let's go ahead. Let's move forward. So then, okay, here I have the integral of a sum. That's then the sum of the integrals. And, you know, I'll bring the constants, and I'll bring the -1 out here on the first integral, and I'll bring the 3 out on the second integral. And these are little simple integrals. Substitution will do fine on those. So the first integral, I'll let u equal 2x minus 1. And then the second integral, I'll let w equal x plus 1. Okay, so here's u. dx, it turns out, will be 1/2 du. So I have u times 1/2 du on the first integral. Second integral, w here, and it turns out dx equals dw. So we got dw. And again, you're just rewriting the integral. So you do it step by step, you know, small steps, small steps. What's the antiderivative of 1 over w?
ln w.
All right, so let me ask you this. Hold on, Franklin, hold that thought. Let's just say you had, you know, this is an aside here. Let's say you had the antiderivative of 1 over x dx. Is it equal to ln of x plus a constant? Is that completely right?
No.
The absolute value.
Absolutely.
Right, and WebAssign will want that. Good, good. So look, we got, man, these integrals here are easy to do. These antiderivatives are easy. So let me go to the next page then. Is everybody good?
Can you hold like 1 more second, please?
Okay, Mandy, sure.
Okay, I'm good. Thank you.
Okay. All right, everybody's good? Okay, well, let's proceed on. So here is our integral, and I factor out the constants. The antiderivative of 1 over u is the log of the absolute value of u, and the antiderivative of 1 over w is the log of the absolute value of w. So we have our antiderivative, but we're not done yet, because remember, the original integral was in terms of the variable x. So we have to take u, and we have to substitute in what u was. Well, u was 2x minus 1. And we have to take w and substitute in what w was for our final answer. W was x plus 1. And so now we have our final answer. Absolutely amazing. Now, partial fraction expansions, there's different ones. And on Monday's class, we're going to be doing some more partial fraction problems from section 5.7. But I'll go to the whiteboard. I can at least maybe we can look at a few types of expansions. All right, go to the whiteboard here. So let's say you had something like this: 2x minus 3 over x plus 1 times x squared plus 5. So the denominator is in completely factored form. So in the partial fraction expansion, you're going to have an x plus 1 in one denominator and an x squared plus 5 in the other denominator. Well, what's going to go above the x plus 1? Well, what kind of factor is x plus 1? What kind of factor in it is it? Begins with an L. Then an I. Giving you a lot of clues here. That's right, Mohammed. It's a linear factor. Has degree 1, right? Has degree 1. Next to the first power there. So what's going to go above the x plus 1? Right, just an A. That's right, OPME and Victoria. So I didn't work it out, Clea, but it's going to be a constant. Now x squared plus 5, what kind of factor is that? That's a quadratic factor. Okay. And what's its degree? Good. Good. Degree 2, second degree. So what are we going to put up in the numerator then? Bx plus c. So bx plus c is a linear, it's a linear expression. The b times x is not enough. We have to also add a plus c. We want it to be as general as possible. So that's an example of some things you're going to be seeing next week. Are there any questions on that? Okay, let me stop the recording then if we're good.